One of the things I wanted to talk about was like it actually bleeds very nicely from the talk before, some of the questions raised in that, especially towards the end. So SLAM is really great, and we're all doing like interesting work pushing the boundaries of localization and mapping. But what after? Like SLAM is never a means, it's always a means to an end. It's never like an end goal in itself. You don't do anything with just like millimeter precise or localization or millimeter precise dense maps. So I'm interested in just using these techniques to do tasks in the real world. For example, in this environment, you might want to ask a robot like, help me find my keys, or like find shoes that match an outfit, or check if pancakes are done. So all of these require capabilities that are beyond what geometric or just spatial SLAM systems provide. And I like to work, so I've done a ton of work on the geometric aspects as well, but I will not talk about them today. I'll talk about the interface, like how do we go from just uninterpretable or like somewhat interpretable points to semantics that will eventually help us do these tasks. And I like to think of this as like knowing what is where. You need to know what is where in the world. And you also need to interpret the context in which these tasks are specified. So all of these tasks are in the context of a broader scene. And then you need to plan, this is what will enable you to plan actions to achieve particular outcomes. So one of the things that psychologists have studied for a while is the notion of world models, like internal representations that we have of the external world that allow us to reason and act. And if you think about it, there's lots of things you can do by just looking at this video sequence. Like you can infer that it's not just a bunch of pixels moving randomly, rather it's a world in 3D composed into objects and so on. You can impute data that's inherently missing in just the pixel stream, like your mind somehow fills it all in. And you can predict what might happen. So what do you expect to see if the camera pans slightly towards the right, even if you haven't seen this particular environment before. And you can then plan actions to achieve particular outcomes. And the more interesting thing for me has always been you can query these representations as to like where is a particular object, or you can do just beyond where style questions. You can, if you have an understanding of physics, you can also ask like what happens, or like what if. And eventually, I think in robotics, we're interested in the how, or like how do we make something happen. And the more interesting longer term question is we want to update these models as newer evidence is obtained. I will also not talk about that last question today. But we are, at least, and this slide was something I made 2 years ago. I was trying to revisit for this presentation, and I figured this did not change. And the notion is if you take any modern like architecture or like task in the image or video or speech space, we are converging onto one linear recipe, which is you just train like large transformer architectures or like whatever newer state space models or so on large data sets. But we are almost exhausting like the web size data we have. And this version of the data pyramid, I think, is making the rounds, especially this year. So there's like, if you want to do tasks that involve 3D understanding, there's fewer data. And as you keep going closer and closer to the real world, there's like fewer and fewer data points, but the task is more and more complex. So you have this issue of you want to solve a much more complex task with orders of magnitude fewer data, and how do you do that? And my central hypothesis in most of what I do is you need to leverage some kind of structure that you know about the world, which helps you learn faster from pure data. It potentially helps being robust when you're veering like outside or along the edges of the distribution. And there's multiple ways in which I can categorize my work. There's at least 3 broad themes. So I will focus today on just the first theme, which is like spatial and semantic understanding, or like knowing what is where in the world. There's a bunch of other things we can talk about offline later. And one of the things I've been interested in, especially since 2022, is how do we best leverage these various levels of the data pyramid? So we have, on the one hand, vision and text. There's orders of magnitude more data, much stronger models. On the other hand, we have like 3D environments that we want to do tasks in. We have fewer data, but how do we bridge that gap? And how do we leverage all sources of data to build these better models? And so these are some examples of tasks that some of these systems enable. So if you have this task of find something to wear to a space-themed party, you have this Jackal robot navigating to this t-shirt which has NASA written on it. And I've seen a few JPL faces here, so interesting to make that connection. And you say find something healthy to eat, and the spot picks up a plastic banana. Well, it's probably unhealthy and it's probably something you can't eat. But in a sense, there's some notion of understanding trickling down, given the context of that environment. And this is an autonomous vehicle driving itself to a place to shelter itself from rain. Or you can play the sound of a door knock and ask where is this sound source in the scene, and you get the pixels or the points corresponding to the door are highlighted. So how do we do something like this on top of SLAM? One of the things we realized, and this slide is going 3 years back in time. So some of these statements have upgraded since. So most SLAM systems we had back then were sort of close set. Even if you were doing semantics on top of a pre-extracted 3D representation, these semantic categories needed to be known ahead of time, effectively at train time. And you could only have one way of querying these maps, and you needed to know that specific class label or ID. And once you change a sensor, you kind of need a new solution to semantic SLAM. So semantic LiDAR SLAM would be different from just monocular SLAM and so on. And at the same time, there were all of these Dino, Clip, and other features in the 2D space coming along. And we tried something very simple to begin with, and that turned out to be very effective. So in this work presented 2 years ago at RSS, we explored the notion of open set and multimodal 3D mapping. So open set, in the sense that we take 3D maps, and these are dense SLAM maps reconstructed by sort of Kinect fusion or point fusion style reconstruction. And these, every point, in addition to having an RGB pixel, at the time our understanding or the way we went about it was, well, RGB, these are just 3 values that do not mean anything to the SLAM system. These are just like 0 to 1, and you just like fuse them without making any special assumptions, and the maps still look reasonable. So why not try them for these high dimensional Clip or Dino features? And for Dino, it's straightforward. For Clip, you still need to jump through a few hoops because Clip is a per image descriptor and not a per pixel or per patch descriptor. And there are some details in the paper about how we get effectively like zero shot without any retraining pixel level features from Clip style models. And we lift these, again, exactly using the same unprojection or fusion mechanism as you would for RGB pixels. And we found that you can do a lot of interesting tasks by just the zero shot lifting. I will again skip through some of these works that, so there was a prior work trying to specifically retrain Clip to do per pixel predictions, which leads to forgetting. And yeah, this was a diet of a grad student close to the RSS deadline. And I had a bunch of objects on the table, and I took these queries and passed them through the existing baselines at the time. But then I found out that when we passed them through our system, since we were not training for this fine-grained task, So when you take a pixel level, when you fine tune an image level model to a pixel level model, you have fewer data. So fine tuning on that smaller data sets results in forgetting categories that are uncommon in the larger data set. But our way of distilling ensures that you still preserve some of that because you're doing this just-in-time adaptation of the model. And with this, we were just able to like live these to 3D VSLAM once you get these dense features. And because it was training-free, we could experiment with a ton of base, clip, and dyno models. One of the interesting finds for us was initially when you started looking around, just taking these features and doing a KNN, k-means clustering on top of them, you would see very interesting semantic delineations. So as you go from the left to right, we're increasing the number of clusters. And you can see that in the first, there are clear clusters for the wall, ceiling, and like the furniture. But as you increase the number of clusters, you start seeing more and more objects. So all of these features seem to be understanding the world in terms of objects. So you could do queries like a place to sit and watch TV, where you take the text query, embed it via clip text encoder, and then compare it, like perform a cosine similarity with the entire map, and you highlight points with maximum cosine similarity. And you can also do, there's like clip models aligned with text, images, and audio. So there's this model called audio clip, and you can play a sound and you can align and figure out which points in the scene might produce that sound. So at this point, like clip is effectively just doing correlations. There's lots of things that clip might not understand about the world, such as like how, so if you have a red toy, clip might get something that is either red or a toy, and sometimes both. So it's effectively a bag of words behavior in that sense, but it was very interesting to see what we could already do with that system. You could also just click on a point and say, get me everything else in the scene. You could do just text-based navigation on a full-size autonomous vehicle on this LiDAR map. So I think it reaches around about, yeah, just about now. And we extended the system. So because of all of these deficiencies in the clip, we wanted to explore what happens if you have better features. And at the time, some of the language models, like vision plus language aligned models with intermediate adapter between the language and the image space started coming about. So we used the lava model for most of this work. And we developed that into an object-based SLAM pipeline that would give, that would decompose the scene into a set of objects. And these were open vocabulary, so you need not have a set of predefined classes. You could also just skip detection, and you could just do, this coincided with the release of the segment anything model, so we could just segment just about anything in the image and then map that in 3D. And we then translate most of these descriptions. So we also have a fused lava feature embedding for each object, and we use that to generate responses to a bunch of canonical questions. So what is this object? Describe this. What's the material? And so on. We have a canonical question base, and then we use that to generate a description that is purely in language. And you can now use this description to do interesting planning tasks where here we have the jackal again trying to find something that goes well with a Ronald McDonald outfit. And the reasoning trace, which is not in the slide, is basically, it goes to this pair of sneakers. It says, well, since the Ronald McDonald outfit is red and yellow, these sneakers are probably a better bet. And again, there could be a lot of errors in translation. That's one drawback of this variant of the system, because effectively you're collapsing the entire 3D representation into text or JSON-like format that the language model reasons over. And ideally, you would want to avoid some of this by trying to maintain the images is one way we have explored in prior work. So this was, there's this one other result where we say, something this person would play with, and a picture of Michael Jordan, and it navigates to the basketball in the scene. Now, yeah, we've extended this a bunch, both work from me and collaborators and also external work to do like 3D scene graph style reasoning, both in indoor and outdoor environments, and also deploy this in human-robot interaction or task planning environments. But one of the things now, when I made the transition from a postdoc in academia to an industry lab, one thing we had access to was a lot more compute. And then the question was, well, can we now start scaling these recipes to 3D? So we have very strong 2D features in the vision and language space. Can we now do some form of 3D pre-training? And this is work primarily led by Paul and Sergio, two of my teammates. And they take the initial like input point cloud with clip and dyno features, just like we did in Concept Fusion, but then do this JEPA, I'm leaving out details of JEPA, but if you're interested in this, you might want to look at a JEPA series of papers. And we use the JEPA objective to 3D pre-training with masked modeling. And then this gives us a lot of leverage in learning downstream tasks. So you can just do JEPA unsupervised, well, self-supervised in a sense, by learning to predict better 3D features by masking out a set of points and then doing masked prediction. And these initial learn JEPA encoders can be fine-tuned to various downstream tasks. So one of the downstream tasks we showed in this paper, which will be presented in a couple of weeks at ICML, is referring object localization. So you could ask more complex queries like the sofa chair by the entrance door, and you can add more referential expressions there or more anchor objects in there. And we saw effectively like a step function change in the performance on raw sensor point clouds due to this pre-training. And all the code and models are available. The inference code and model checkpoints are available. One of the things we also did as part of this, again, touching upon the evaluation aspect of this workshop, is we collected sort of the largest referring expression benchmark to date. Because we also want to evaluate like how well we do on just general purpose text-based object grounding tasks. And I want to flag Ada, who primarily led the curation of this benchmark. And we also have a web demo where you can try out some of these queries on scenes that you already have. So just a few takeaways in the end is like, you can distill knowledge from these multimodal models using structural prior. So we are effectively leveraging structure in the form of 3D representations to use heterogeneous data from all levels of the stack. So you can do 2D or 1D pre-training at web scale and use those features to initialize or bootstrap 3D pre-training, which then allows you a lot more flexibility in what you do with your robots in the end. So with this, I just want to acknowledge a few of my collaborators, and then there's also a ton of stuff to do, but I will stop at this point and take any questions.
Me. One question over here. Thank you for the amazing talk. I absolutely love this work. You also mentioned a potential connection to like physics and prediction of the scene. How far along is this already, and how easy is it to process these, say, pre-trained point cloud style representations from JEPA for, say, prediction or embedding physics?
Yeah, so I would say we are there in terms of all of the raw representations or recipes we need for pre-training, but one missing piece is like to scale to 3D. We had a like order of like tens of thousands of 3D scans of indoor environments. So for the Locate 3D dataset, we just took a bunch of these like Scanit++, ARKit scenes, and a bunch of other datasets that were available internally, and then we could scale training. But for physics, you need 3D point cloud reconstructions and also like dynamics. So I see that as a bottleneck, but now we are seeing very interesting breakthroughs in perception where you have these any point trackers and like very accurate depth. I saw foundation stereo get mentioned in one of the talks earlier. So with all of that, we may be able to generate real data. Well, there's the alternative route of just train in simulation where you can get infinite data, and but the question always is, will that generalize? So there's the opposite spectrum of let's train on purely real data, but then that's hard to capture. So I think we are going to meet somewhere in the middle, maybe an equal mix of real and sim data. I also saw the Groot paper getting a mention. So they do a 1:1 mix of sim and real. So maybe the solution is somewhere in between. I think the models are there. JEPA as a training objective seems to work. It's unstable. So I think I've heard it's an art to stabilize training with JEPA, but we are still looking for the right data to train it on.
Thank you.
Thanks for the great talk. So recently there are some kind of 3D reconstruction foundation model like the VGGT. I just wonder, so we got best paper, which is also from Meta. But this kind of foundation model only deal with the geometry information. Do you think that it's also possible to integrate such kind of open vocabulary semantics information into such kind of 3D reconstruction foundation model?
It is possible, and I think historically they've just been treated as separate problems because of just like a different focus of each set of researchers you talk to. But with the models becoming more and more capable, I definitely see a path to where now people are starting to think about inherently multitask models. So 3D reconstruction as a task is getting closer and closer to being solved in a restricted set of environments, or at least in a set of environments that we would care about very often. It will never be like, it's not completely solved now, and I think there's still a long way to go before we can completely solve. But with the solutions we have today, we can already start building very interesting integrations. Like sort of you mentioned VGGT, and I think Duster really kickstarted this series of papers. And we are also seeing like integrations with SLAM, a couple of papers already on that. So I think it's a matter of time before other things come.
Thank you very much, Krishna.